Hello, everybody. I will today talk about Josephson junctions and their applications. And here in this presentation today, we will try to answer few main questions. And today, first, we will talk about actually superconductivity, because Josephson junctions are contains of superconductors. And after talking about the properties of superconductors and superconductivity, the theory of superconductivity, we will talk about actually why pure superconducting materials are rather useless. We don't have many practical uses for superconductors. And the reason is, well, we will talk about. So then we will move on to the Josephson effect and try to understand the discovery and the prediction of the Josephson effects and what makes the Josephson junctions useful. And finally, we will talk about the applications of these junctions and where we can use Josephson junctions and where they are being used right now. But first, the discovery of superconductivity. So in 1908, Onnes liquefied helium, which started a new chapter in low temperature physics. So they discovered that mercury has no resistivity at some temperature, and its resistivity has dropped to zero. This was discovered in 1911 by Onnes, and he called this state of zero resistivity superconductivity. So now we should talk about what zero resistivity is and how superconductors show the behavior of resistivity depending on temperature. So here's a graph of resistivity versus temperature scale for normal metals and superconductors. Of course, this is not a scale. This is just an arbitrary thing to show you how they behave. So here, this is the critical temperature of a superconductor, and this is the real data taken from Onnes work. So this was the mercury, the point where mercury showed having resistance. That was 4.2, as we talked about. And this temperature that we lose the resistivity, or where we see the phase transition, is called the critical temperature of a superconductor. So in a normal metal, what we see is a saturation, but in a superconductor, at some critical temperature, we see a sudden drop, and then we see no resistivity at all. So in a superconductor, we also don't observe any currents inside the material, but these supercurrents with no resistivity forms on the surface of the material. And maybe it is worth mentioning that the zero resistivity, because resistivity is, I mean, talking about this physical meaning of zero resistivity, because when we say zero, it is a perfect physical meaning, correct? When we have, like, we could have 2 apples, 3 apples, or 0 apples. But here, resistivity is something we measure. So how can you actually measure zero? Or how did Onnes did this? They did this by actually measuring the decay of the current, because if your material has a resistivity, the current you have through the material should decay in time, and you should lose this energy to dissipation. But in superconductors, the decay within the, of course, error of the experiment, so there is some, we can only put a limit on, like, if there is a resistivity, how high it could be. So that is pretty small, and now today we can almost confidently say that is zero. So they made, the Leiden team made 2 discoveries actually without realizing one of them. Yes, they did discover superconductivity, and they also, when they liquefied helium below some temperature, they observed a helium, a phase transition of helium without realizing. So later in history, Pietro-Capizza discovered that this phase is actually a superfluid, and they are analogous with each other, these phases, in many ways. And we shall actually mention how they are analogous in some video, in a slide after a few slides. So here you can see this is a helium in its superfluid phase. So if this were a superfluid, some of the like a drop of the superfluid would creep out of the material, the container here, and then keep going through it and then drop here until there is no superfluid left. It has also zero viscosity, and this is the way they're analogous to each other. So in one way, the superconductor has no resistivity. The charge carrying particles inside the superconductor has no resistivity, and in superfluids, the viscosity is zero. So the resistivity to flow is zero. But as I said, we will see this is more than an analogy. So now we will talk about a property of a superconductor, of superconductors, the Meissner effect. So this is what happens when we apply a magnetic field to a superconductor below critical temperature, of course. So it's in superconducting state. So what we observe is we see that the superconductor actually a perfect diamagnet. That is, it forms supercurrents on the surface of this material and excludes all of the magnetic field inside it. So in SI units, its susceptibility is -1. And in CGS, it's -1/4 pi. So this is rather odd for other diamagnets, because the normal diamagnets we have susceptibility so close to zero. So this is a perfect diamagnet, and it's a very important property of the superconductors, if not more important than zero resistivity. And this was discovered by Walter Meissner and Robert Oschenfeld in 1933, experimentally. So here I should briefly talk about the London equations. So here are the two equations, which I won't go into detail, but they have the electric field, which we can measure, the magnetic field, which we can measure, and the current change and the curl of the current here. And there are some constants here in these equations. So we have the electron charge, the mass, and the number density of superconducting carriers. So here, so this number density of the superconducting carriers, what are these superconducting carriers? We will talk about them in a second, but we should talk about their importance, these London equations' importance, because they were the first successful, one of the first successful theoretical equations which explains the behavior of superconductors, came from the London brothers, Fritz and Heinz London. So these are phenomenological explanations, because the aim of these equations were to explain the experimental data rather than predicting what will happen. But they were pretty successful at explaining them. And they also suggested a penetration depth of the magnetic field. So in Meissner effect, we have seen that we don't observe any magnetic field inside. But with the London equations, now we know that there's actually a penetration depth of this magnetic field inside this material through the surface. This is depending on these parameters here. So these constants and the number density of superconducting carrier, which is changing from one superconducting to another, but the typical value of the penetration that is 50 to 500 nanometers. So they were good to use, and for example, the penetration depth is something you should be careful of if you want to make a superconductor. You shouldn't make it too thin. But they fall short on explaining the microscopic origins of the superconductor's behavior. So here we will talk about something called the trapped magnetic flux. Okay, so we will consider the case where we have a superconducting ring. This is a hollow ring with thickness, of course, larger than the penetration depth. And here we apply magnetic field on this superconducting ring, but not superconducting, I'm sorry. This is a superconductor, but it is now a normal metal. That is, its temperature is higher than the critical temperature. So when we apply magnetic field, these magnetic lines will penetrate through that, and we will observe what we would observe in a normal metal. But when we cool it down to the superconducting state, a consequence of the Meissner effect is, as a consequence of the Meissner effect, these magnetic field lines will not be able to penetrate through it, but go around it, and we will observe some currents on the surface of this material. So there will be magnetic field outside the material, inside the material, but not, I mean, inside the hole, but not inside the material itself. So something rather odd happens if we now turn the external field down. So what happens here is we observe a magnetic flux inside the hole, although we don't apply any external magnetic field. These lines, these magnetic field lines are, I mean, the flux inside the hole is supplied by these persistent currents which are formed on the surface of the material. So to understand how we went from B to C, you could consider the line integral of the electric field here. So by the induction law, we know that, by Faraday's induction law, we know that the magnetic flux change should be equal to that integral. But here, since this is a conductor still, the electric field lines are zero inside this integral. So then the magnetic flux cannot change. So then, once we go through this, the magnetic flux doesn't change, and we will have a trapped magnetic flux. Okay, so investigating this case further, we see that classically we could expect any value of magnetic flux could be in this ring, whatever we put. But that won't be the case if we investigate it quantum mechanically. So I know I shouldn't show so many calculations, but I wanted to give you an idea of like the underlying theory, understanding the underlying theory, and recover some important characteristic properties which can be used in the experiments. So to do that, actually doing some work is going to be necessary. So here we have an expression which is looking very complex, but it's just actually, I'm sorry. This is just the probability current density, which is with the brackets inside are the quantum kinetic momentum operators for a particle in an electromagnetic field, where A is, of course, the magnetic vector potential. So here, okay, so this is what we could know from a quantum mechanics course. But here, this is an order per meter for a superconductor. There are two order parameters here, which one of them being the phase, and the other is the current density. These are known as the Ginzburg-Landau order parameters introduced by them. So here, if we plug this in, of course, I won't go into detail on how to solve the algebra here, but if we plug this in inside the current, what we would have is the current would be equal to this expression here. Again, we have the charge of the superconducting carrier divided by the Planck's constant coming from the momentum here, charge density with the divergence of the phase and the mass of the particle. But inside the superconductor, we know that the current is zero. So what we would have is a relation between the divergence or the change of the phase and the magnetic vector potential. So this is a good relation, and we will actually use this relation when we talk about the applications of the Josephson junctions. So here, now we know the magnetic flux through a loop is the integral of the magnetic vector potential on the loop. And if we use this relation for this integral, what we get is h bar over the charge with the integral. But remember where we are taking this integral. Here, we just had a ring, correct? So this is just a ring. So divergence of this integral would be just n2 pi, any integer multiple of 2 pi. So now what does this tell us? Okay, physically, so the magnetic flux through this loop, through this ring, can only take certain values of n times h over q, because h is just the Planck's constant and q is the charge of the charge carriers, which could be electron, hopefully, n times n. So then classically, we would talk that any magnetic flux could be here, but quantum mechanics tells us the flux is actually quantized inside this ring. Okay, so this result actually calls for defining a magnetic flux, a basic unit for magnetic flux. And Fritz London, one of the London brothers who came up with the London equations, did a similar calculation like we did, and predicted that the basic unit of flux should be h over e. So he just put, I'm sorry, I messed up. Okay, he just put e here. Okay, so he said, so this is like a superconductor, and the charge carrying particle should be the electron, and its charge is e. So he said the basic unit of flux, the magnetic flux, should be h over e, which is about 4 times 10 to the minus 15 Tesla meter squared. Or in CGS units, this would correspond to 4 times 10 to the minus 8 Gauss centimeters squared. So this was this effect of magnetic flux quantum, magnetic flux quantization was observed by Deaver and Fairbank. And I'm sorry. Okay, they were observed by two different experiments independently, but so this data is from Deaver and Fairbank, and I forgot to mention that here. I'm so sorry for that. But this the important thing here is they discovered this basic unit of flux is h over 2e, not h over e. And here the data from the experimental evidence of magnetic flux from their paper, and the data is pretty precise that they have values, the data points would correspond to h over 2e here and minus h over 2e here. So, and this is also another picture I got from their article. And here they mentioned that this was originally suggested by London and Onsker, but they are pretty wrong. So there is some interesting reason the charge of the superconducting carrier is 2e rather than e. So to understand that, we will talk about something called the BCS theory, which is the first successful explanation of superconductors, a microscopic explanation of superconductors, how they work on a microscopic level. So this was done this was proposed in 1957. So historically, this is a really long time, unless the discovery of superconductivity at 1911. So the missing ingredient came from actually Leon Cooper. So in the paper called bound electron pairs in a degenerate Fermi gas 1 year before BCS theory was published. So he proposed that due to interactions between electron and lattice vibrations, which are called phonons, 2 electrons could have a net attraction between them. And this attraction would overcome the Coulomb repulsion. So it's a net attraction. And furthermore, he used Fermi-Dirac statistics for electrons, how electrons behaved. And he showed that the paired electron state would have energy less than Fermi energy of the material, which would imply this bound state of two electrons will be formed at low temperatures. So they will be formed, and they will be formed only at low temperatures. So this is a Feynman diagram for, so yes, also we now call these bound pairs Cooper pairs, of course, which with good reason. So here we have a Feynman diagram for two electrons interacting with each other with a phonon interaction. Of course, this, as all Feynman diagrams do, they have messy equations with each branch there. So we shall talk about Cooper pairs before ending our discussion on the BCS theory. So we said bound state. So this calls for a binding energy of the two electrons. So this binding energy will create an energy gap between the occupied states and the unoccupied states. We have shown in our lectures what these graphs are. They are the, here we have the distribution density, let's say, and we have the energy here, which is the like a reduced energy. Here we have the energy equals to energy Fermi, so that's why here E minus EF is 0. And at higher temperatures, the formation of Cooper pairs are they won't happen above Tc. At T equals T0, the energy gap will be visible. So there will be an energy gap. I mean, it will be 0, but the second we go below Tc, we will have an energy gap, which will not let electrons pass from the empty state to occupied state, and because that energy gap will make those states impossible to attain. And so this energy gap happening at Tc also suggests a phase change. And above Tc, due to thermal excitations, we won't see any Cooper pair formations. So here, maybe we could also mention that since this theory is depending on the vibrations of the lattice, this could also explain or give an explanation for why good conductors like copper and gold don't become superconducting. So when we are looking at bad conductors like worse than gold and copper, we see that they become superconducting. We will also observe, like I will give a data for you a few slides ahead, show which elements we have superconductors for. But this could be a reason that the Cooper pairs won't be forming in gold and copper because they lack this required lattice vibrations. Okay, so finally, before we finalize off our discussion for the theory of superconductivity, a little bit of quantum statics. So here we have, okay, now we are hopefully convinced that we have a Cooper pair formation at low temperatures. But why do the Cooper pairs behave differently than electrons? So why the two electrons, when they become together, why do they act differently? Okay, so we have already mentioned that Cooper used Fermi-Dirac statistics, and the particles which are governed by Fermi-Dirac statistics are called fermions, such as electrons, protons, neutrons. And the particles which are governed by a different quantum statistics, which is the Bose-Einstein statistics, they called bosons, such as photons, gluons, and Higgs particles. So a very important difference between them is one of them obeys, fermions obey Pauli exclusion principle, whereas bosons, they don't really care about the restrictions placed by the Pauli exclusion principle. So, but we are still missing how two electrons come together and they act differently. So one last thing to mention is a composite particle which contains an even number of fermions behaves like a boson. Now that a Cooper pair contains of two fermions, which are two electrons, they could act like a boson. And at low temperatures, due to bosons not caring about the Pauli exclusion principle, they will be condensed to the lowest possible energy, whereas the fermions, as we have seen in our lecture, they will occupy these states up until they reach the Fermi energy. So they behave very, very differently at low temperatures. So this state is called the Bose-Einstein condensate, and both superfluids and superconductors could be an example of Bose-Einstein condensate, but as I said, I won't, as I promised, I won't go deeper into this subject, but I will talk now about why we cannot use superconductors, for example, in a circuit. So there is a critical field of a superconductor, which I purposefully avoided up until now. So now that we know how cool these superconductors are, there is this, with the Meissner effect, like they expulse the magnetic field we apply to them. They don't let it in. But if we pass a certain critical threshold of this magnetic field, superconductors say, okay, enough is enough. Now I will kill the superconductivity and I will start letting in magnetic field. So this is not good for us because there's a relation between the maximum current that we can pass through the superconductor and the maximum critical field that we can pass through, that we can apply to a superconductor before it loses its superconducting state. And this critical temperature is also, this critical field is also a function of a temperature. So if we increase the temperature, the critical field, the field we can apply before losing this superconducting state is also decreasing. And if we hit the critical temperature, of course, we cannot apply any magnetic field in the superconducting state. And there's a relation, as I said, which was drawn by Silsby. Onnes knew that they could have applied, that there was a threshold for this critical field, but he couldn't have drawn the relation between this. And Silsby did it, and with this equation, which again we have seen in class, and this tells us that there is a limit that we can pass through a superconductor. There's a limit for the supercurrent, and it is related to the magnetic field that the superconductor can endure. So this is very bad for practical purposes because consider that you have a superconducting wire, and you want to pass, like you want to apply voltage, but you cannot, because if you try to do that, the current would try to go to infinity, but it cannot, because the second it passes through your critical field, you would lose the superconducting state and you would just have normal metal piece of wire. So now, as promised, I will also show some data. So these are certain elements like lead, mercury, and tin, and they show some, as I said, C is a function of temperature, and as temperature increases, this H is decreasing. And here at H equals 0, we can see the critical temperatures of certain elements as well. Like mercury is very close to 4.2, which is which is what Onnes observed. Okay, so there are two types of superconductors, and type 1, and I will very cut this short here because we don't really care much about this, but we categorize superconductors on how they lose the superconducting state. So we apply field and we check on how they are losing the state. So type 2 superconductors go through a mixed state here, where there is a magnetic field penetrating through that, through them, and there are some vortices which with current forming around them, because this is the surface of the superconducting layer. So there are two critical fields for type 2 superconductors, but for a typical type 1 superconductor, we just lose the superconducting state at once. Okay. So now we will talk about Josephson junctions, and I think this is a good place to give a break, and we will discuss this on the next section. Okay, so welcome back. Now we will talk about a setup where we have two superconductors which are connected by a thin layer of insulating material, as in this figure shown. This arrangement is now what we call a Josephson junction. So Josephson analyzed this setup and what might happen at a junction between two superconductors, and he discovered that a number of strange phenomena should occur. Because if the insulator is thick, that the electrons cannot get through, but if the layer is thin enough, there can be appreciable quantum mechanical amplitude of electrons to jump across, then this is just another example of quantum mechanical tunneling. So here, we should be able, so we know now that there are Cooper pairs here, and there are Cooper pairs here. So in a quantum mechanical observation would tell us that a Cooper pair should be able to tunnel through this. And Josephson predicted that a supercurrent, which means that this current, the charge of the current is carried by Cooper pairs. And a supercurrent here is flowing through the junction as with this equation. Here, this delta represents the phase difference of these two superconductors. Here, these are the Landau parameters that we have introduced. So this is now what we call a DC Josephson effect. Why? Because this phase is given. Like, we cannot control when we have a Josephson junction. We measure this, and we measure the critical, we measure the current, and the maximum amount of current that we can pass through is the critical current of the superconductors. And since phase is not changing by its own, there is a DC current. So that's why this is called the DC Josephson effect. So this is the moment that we have been waiting for, because now that we have an insulator inside, now we should be able to apply some voltage across these junctions. So now, to obtain the other effects of Josephson, we shall do some more calculations, quantum mechanical calculations. So, but I will walk you through them. So here, what do we have here? Okay, so we have the change of the wave function on the left with respect to time should be equal to, if we let t be the like the tunneling rate of the Cooper pairs, then they should be equal if you don't apply any voltage, right? The change on the left should be how many Cooper pairs are coming from right. Perfect. But if we have voltage, then the expression should change. Now that if we were doing full quantum mechanics, we could have taught this like the electromagnetic force operator. But here we will just assume that if we are given that there is voltage across these junctions, that the left-hand side and the right-hand side equations will be symmetric like this. So now we have two equations which look rather similar. And again, for the left and right, we have the wave functions like this, where here now what we know the charges, we can now say, instead of some density, we can say Cooper pair density on the left and Cooper pair density on the right. Okay, so again, we will plug this in and try to solve for actually this equation. The rate of change of the phase comes from the imaginary part of the solution. So here we assume that, so where did the t go? Here we assume that the voltage is not so big, that the Cooper pair densities are almost equal to each other. So that's the assumption we made here. And this gives us the rate of change here as 2 times the electron charge, which is 2e. So times the voltage here, the voltage we are applying, divided by the Planck's constant. So since we are interested in superconductors, as long as you see E, you should see a 2E next to a 2, an E next to the E. I'm sorry, a 2 next to an E, because the charge of the superconducting carriers are 2E, not E. Okay, so integrating, we get the phase difference equals to some constant. This is actually the constant that I said that we cannot control, minus t times 2ev over h bar. So here we had this in the DC Josephson effect, we had the phase difference of two superconductors. So if you plug that in, what we get is, now we know this as AC Josephson effect. So this is AC because if we apply a direct voltage, the current is oscillating through the junction. So here we should point out that this is our angular frequency for the oscillation. And to understand how fast this oscillation is, we should maybe give some numerical value. Let's give a really small voltage, like 1 microvolt. So a DC voltage of 1 microvolt corresponds to almost 500 megahertz. So this is a very big amount of frequency that actually, when we apply DC voltage, the oscillation frequency is too high that we get no amount of net current. So when we observe the Josephson effects, which was done 1 year after Josephson predicted them. So Josephson predicted them in 1962. And the first observation came from Anderson and Rowell. So they said, in the name of the article was Probable Observation of the Josephson Superconducting Tunneling Effect. So I read the article a few times actually. So I think the probable there was there with good reason, because I couldn't really see the effect in what they have done, but one should admit that yes, there is an anomalous behavior. There is a weird behavior near zero voltages of the current. But I won't spend so much time explaining the data here, but because we should focus more on what Safiro did. So Safiro's title was Josephson Currents in Superconducting Tunneling. and the effect of microwaves and other observations. We will come to other observations in our next slide. But first here, let's try to analyze and understand this. So although Safiro did a very good work on the experimentation, unfortunately he did it at any scales, so I did that manually. But here we have the 0 voltage area here. I'm sorry, 0 voltage area here. So when we have 0 voltage, we can observe that there is a spontaneous current. It's spontaneous because we cannot control this, but this current can take between any value of the critical the critical current and the minus critical current here. It can take any value. And once they started to increase the applied voltage, what they had is no net current. So you cannot observe any current up until you apply some more voltage, which gives you current, some net current. But here are our DC Josephson effect, and here where we have 0 net current is where we have the oscillation and AC Josephson effect. Okay, so now we will talk about the inverse AC Josephson effect. So with many things, there comes the inverse effect of it. So what we had in the AC Josephson effect, so we had, okay, going back to that. So what we had is we applied DC voltage and we observed a frequency we observed the radio frequency here. So since charges are accelerating here with this frequency, we actually had a radio wave emitter when we applied DC voltage. So doing this backwards in the inverse way would be, if we applied microwave radiations to a Josephson junctions, we should be able to measure a DC voltage across these junctions. And this is what Safiro did exactly. So here, the tunneling current of DC Josephson effect no longer occurs at 0, but rather 58.8 voltage. So this is the same voltage where we lost the AC effect. So, and the reason is they actually applied a resonance frequency. That is the frequency they observed when they applied this voltage. They now applied the frequency back at the junction, and they observed the same voltage shift in the IV characteristic. So this is, that is the HF divided by 2E, F being the frequency, applied frequency to the junction. So this frequency they applied was actually 9.3 gigahertz, if I'm not mistaken, and then they actually swept through that and found this was the sweet spot for the resonant frequency. Okay, so now we shall observe some characteristics of the Josephson junctions. So in the presence of magnetic field, we have such behavior. So this is the current passing through the junction. So if you wish, this is the maximum amount of current that you can pass through the junction. So Josephson tunnel current, we shall call it, is dramatically affected, as you can see, by applied magnetic field, because the amount of magnetic field we are applying is rather low. And the effects were observed for the first time by Rowell, who claimed that they have a probable Josephson effect. So now they did a very good job on observing the effects of the sensitivity of the Josephson tunnel current. And as they used a lead insulator and a lead junction, and their data, as you can see here, pronounced minimas and maximas for the current. And here, where minimas occur is the magnetic flux at an integer multiple of h/2e. Can you recall that? This is the magnetic flux quanta, and that is no coincidence. So actually, Josephson in 1962 predicted a similar characteristics as well. This is again where I took a piece from his article. He said that the cancellation of supercurrents would start to occur when the amount of flux between the films, including the penetration regions, what we call in London equations, and when they became of the order of a quantum flux, hc, c here is the constant term like n, hc over 2e. So he also said that this would be about for typical dimensions, because the flux is depending on the area of your film, would be 0.1 Gauss, which is not so off with the data we have here. So, okay, now we will do more calculations. So first, but before we do these calculations, I will introduce what is called the kinetic inductance, which is normal inductance comes from, of course, the magnetic flux, magnetic field, but the kinetic inductance actually comes from the kinetic energy of the moving charges. So here, taking the derivative of the AC Josephson effect gives us back this. So now that we have the quantum flux, the magnetic flux quantum, we can also represent this like this. Represent the change of the phase with respect to time like this. So here, this would yield rearranging the voltage across the junction like so. So this is the quantum flux. This is 2 pi times the change of the phase with respect to time. So here now we will we can define a flux like so. Here, this is the since this is a phase and this is also like an angle, so we can define this flux as the magnetic flux quantum times the phase difference divided by 2 pi. But if we define this, what we would get looks very similar to Faraday's law of induction. Again, I repeat though, this is an analog of Faraday's law of induction because the source is not magnetic energy, but the kinetic energy of the tunneling Cooper pairs. So since the Cooper pairs that are tunneling has a kinetic energy, since they accelerate, and we can define a kinetic inductance term like this. Okay, so moving forward, now we will define two characteristic parameters for the Josephson junction, which are actually really crucial to explain a Josephson junction that you have. So here now, taking the partial derivative of the DC Josephson effect, and if we define the phase difference, here we have the DC Josephson effect, and if we take the derivative of the DC Josephson effect here, so we have the cosine, and we already defined the change of the phase with respect to time like this. So now we can apply a chain rule and arrive at this result. So this result here will, this looks like an IV equation for an inductor with inductance like this. So if you can see here, there's a change of the current and there's a voltage here. So this term here would be the 1 over inductance. So I'm sorry, this is the inductance itself. I'm sorry. So inductance times the voltage is the change of the current with respect to time. So here, now that we have the constant term ahead of the cosine term, now we can define the Josephson inductance as quantum magnetic flux quantum divided by 2 pi critical current IC. And to define Josephson energy, we will use DC voltage, and so maybe before going further, so since these are constants and IC doesn't change much, a magnitude of a typical Josephson induction is between 1 to 10 nanohenry. Okay, so now similarly, we will calculate the Josephson energy since the energy will be equal to the work done by the function, and we have here a voltage and a current. We can just take the integral here and plugging the relations in here. So we apply IC here and VT here, and we take out the constants and take the integral from some delta 1 to delta 2. This would yield the difference in the energy would be some constant term times the difference in the cosine of the function. So then we can express the energy like so. Again, this looks very similar to this, and then we can name this constant term as the Josephson energy E sub j. And they are both changing with the cosine of the phase difference of the junction. So also the relation between them can be put using the squared of the critical current. Now we will talk about, since we have the energy here, we will talk about the energy levels of a Josephson junction. So here we have we wrote the phase like this, which we defined the flux, if you recall a few slides back. And now we rewrote the energy in with respect to magnetic flux. So approximation for this cosine term for very small magnetic flux with the Taylor expansion, it can be written like this. So this is like a constant term plus 1 minus a squared term. So here we can see various approximations of this term. And since this is quantized, the magnetic flux is quantized, we will have energy levels here. But since this is a parabolic function, these energy levels will be in an unharmonic spectrum, similar to the energy levels of an atom rather than a harmonic oscillator. Okay, so I mean, this is really important because of the reasons we will see in the applications of Josephson junctions. But what you should remember about this is once we approximate the magnetic flux for small values, we get unharmonic spectrum for the energy levels of this junction. Okay. So now, before finalize here on the Josephson junctions, we will talk about different types of Josephson junctions. And here we will talk about the proximity effect. And I have this figure here. Here we have a superconductor on the right, and this is just a normal metal here. So this is actually an interesting junction that we have investigated so far. I mean, different than the ones we have investigated, because we always had S, an insulating barrier, I, and S, which is the other superconductor. But here there's a normal metal. And here the proximity effect means that if you have a normal metal next to a superconductor, you will observe the Cooper pair density is lowering, and the Cooper pair density in the junction is increasing. So you will have tunneling in normal metal as well, and actually rather more tunneling than you would observe in an insulator. So here, for example, this is our normal SIS junction, which is a superconducting electrode and an insulating barrier and a superconducting electrode again. But a different type of conductor would be, so this is now, they are now connected through a normal metal with a separation distance d. So due to this proximity effect, these the layer on the normal metal becomes weakly superconducting proximity layer as well. Used to be a normal metal. But now, if this distance is small enough, then you would again observe Josephson effects in this type of junction as well. And finally, we will talk about a constriction here. This C stands for constriction. So here we have actually just only superconductors, but here this is like a narrow path of a superconductor. And again, this acts like a weak link. Okay, so these are all called weak links. Here the normal metal, here the insulating barrier, and here the constriction. So we can decide how thick we should make our separation depending on the proximity effect of our modeling. So for example, if you have an insulating barrier, it should be at around 30 angstroms. But for normal metal, it could be order of few microns, for example. Okay, finally, we will talk about the RCSJ model. This is called a resistively capacitance shunted junction model, and sometimes called just shunted junction model. This is actually one of the most basic circuit models, which consists of a Josephson junction. And since we know the current characteristics of the Josephson junction, we can actually write the passing current through the circuit. So here you can all see this is the current through the capacitor, and this is the current through the junction, and this is current through the resistance. But here, to make a full analysis here, it requires some level of quantum electrodynamics. So we will not go into details here, but we will give the result, what is called a tilted washboard potential for the circuit. And this is, here we have the reduced energy of the, the energy of the circuit divided by the Josephson energy. And here we have again minimas occurring at the multiples of pi and maximas occurring at odd multiples. I mean, even multiples of pi, the minimas occurring, and at the odd multiples we have the maximas occurring. So now we are ready to talk about the applications of Josephson junctions. So there are many applications of Josephson junctions in actually many different disciplines. So they're already a direct topic of solid state physics, as Sana just said, but the Josephson effects are also used to understand the behavior of, for example, quantum gases in other fields of theoretical physics. And also in engineering, they can be used, as we talked about, microwave receiver or a microwave emitter, and using the AC Josephson effect. And of course, in computational engineering, they're majorly being used as quantum information devices. So today we will focus on two major applications of Josephson junctions. One of them is called a squid. Here you can see a squid magnetometer manufactured by Quantum Design, which is a brand very well known in our research group. And here we have a picture of a qubit, actually 5 qubits, which is manufactured by IBM. Okay, let's start with squids. So the very first thing to know about squids is that they have no relation with octopuses and calamari. Okay, so they stand for superconducting quantum interfering devices. So here they are sometimes also called DC squids, and they are used for detection and measurement of magnetic fields. So they are magnetometers. And they are called DC squids because they make use of the DC effect. So here in this picture, we have 2 Josephson junctions connected in parallel. And when we apply magnetic field through this loop, we will observe a phase change in the function in the junctions, and the currents going from up here and down here will interfere with each other, hence the name of the device, and they will create maxima and minima for the current. And we will find the current by measuring, for example, voltage across the device, and then deduce the magnetic field applied. Of course, while providing high precision, so they are very precise, but they cannot be used for measuring like large magnetic fields because you would lose then the effect. So that's why using a high TC, for example, a type 2 superconductor, would be much more convenient if you are using a squid. So now the final bunch of equations that I will introduce today is to explain the working principle of squids. So please try to bear with me here. So, okay, of course, we can guess that the working principle is based on the magnetic flux quantization, since we have a loop and magnetic flux going through it. So we will use this result here that we have found when we are discussing the magnetic flux quantization. So here, this to help you remember that this relation is this expression is giving us the relation between the phase difference of the junction and of 2 superconductors and the magnetic vector potential A. So here, what I did is I said, okay, let the phase difference for this junction be delta A, and let this phase difference for this junction to be delta B. And then I can find the, for the complete loop, by taking the integral of this term and then merging them together, I can write this expression. But then again, integral around the loop, around this loop, the complete loop now, of this closed loop of the vector potential would just give me the flux through the potential. So now I have a relation of the phase difference for both of the junctions and the flux going through the loop. Okay, now that I can, using my knowledge and doing some trigonometrical tricks, I can arrive at this expression of the J total here is 2 times the J0, which is the minimum current or some constant current we apply in the junction. Sine of the constant phase difference of these junctions, which I have no control of. Again, 2 terms I don't control. But now a cosine of the flux through the loop, which I can control. So instead of measuring the junction, what I can measuring the current going through this device, what I can do is find the maximas of the current, which will happen at an integer multiple of the flux is an integer multiple of PHYE, which is cool. And this is a data taken from Ford Motor Company. So they are here using a squid, and when they apply magnetic field, which is again very small magnetic fields, here they have some maximas and minimas, and again they are losing the effect when they reach even a small magnetic field like 300 milligauss. But here they have a very good knowledge of which, like a good precision of what magnetic flux they are sending through the junction. Okay, so this article is actually something very perfect because it puts together every effect that we have discussed. So this article uses Josephson effects because it uses squids, and it measures the Josephson effects of a Josephson junction. And it's such a junction that is called here in their article they called an ultra small Josephson junction. This smallness comes from the capacitance of this junction is comparable to the Josephson energy of the junction. So the energy comes from the intrinsic capacitance of this junction is comparable to the Josephson energy. And this is important because we are using this energy I'm sorry, we are not using this energy. We are using such junctions in quantum information devices when we are building qubits, for example. So here we have the data they measured here is actually for 0 volts, they have the DC effect, and we can clearly see the net current here, and they zoomed up here, which is for different temperatures. And of course, the temperature is here is very low. They are working at 34 millikelvins for the best precise measurement. And so this, I won't go into details of their explaining their circuitry, but you're free to check their paper. Okay, so we will now talk about qubits. So in a classical bit, the value of a classical bit can either 1 or 0. So it cannot take both of the values. So, but in a qubit, the value of a qubit is actually a superposition of 1 and 0s. So here, we will now talk about what can qubits do, because if you have a computer, a quantum computer running with using quantum bits, they can solve certain challenging problems for classical computers much faster, and sometimes a problem that could take years, maybe decades, could be solved with a quantum algorithm which uses a qubit as a processor. But this is not true that a quantum computer would be superior to a classical computer, because they will be, if we have a great quantum computer that uses many qubits without error, then this would be only helpful for solving certain problems faster rather than doing anything that a classical computer can. This is not the truth. So here we have a representation for a quantum bit, which is a Bloch sphere. This is called a Bloch sphere. Here we can see the superposition of 1 and 0 in a three-dimensional complex plane. And here, once of course, in the quantum state, in the superposition state, the quantum bit can be anywhere on the sphere, on the surface of the sphere. But once we measure the data is either 0 or 1, and this data is stored in a classical bit. So actually, even to store the data we measured on a quantum computer, on a qubit, is actually stored in a classical bit. So even by nature, we need classical computers to use quantum computers. So, but a question for a solid state physicist is, how can we make physical qubits? So we need small dissipation, because if you have a quantum information stored in somewhere, you cannot lose this information, because once it is lost, it is gone forever. It's not like classical information, because once a system collapses, there is no going back. It's that the information you had is gone. You either get 1 or 0. You have no way of knowing what you had before. This is actually a very important dynamics for quantum cryptography. So we have to have isolation from the environment, because if your system is interfering with the outside world, again, this would or could result for your system to collapse. And you need a two-level system. So you need a system which can take only two values, rather like in comparison with an atom. So an atom can have be on different energy levels, but for a system to act like a qubit, you need a two-level level. So the first two criteria actually just comes natural with superconductors, because in a superconductor, rather than small dissipation, you have no dissipation at all. You have zero resistivity. So that's checked. And in order to have a superconductor, you generally work at low temperatures. So they are isolated from the environment in order to keep your material or system in low temperatures. So the two first things are checked by superconductivity itself. So what about a two-level system? So here we ask the question, can nonlinearity of the energy levels of the Josephson junction help? So here we see a photograph from IBM. This photo they shared consists of 4 quantum bits and 4 quantum buses and 4 readout resonators. So, okay, so quantum bus is not important to us. It is required to pass information between 2 qubits. So if you have a chip which contains multiple qubits, you need a quantum bus as well. But a quantum resonator, readout resonator, is actually required to increase the energy level, or apply gates to that, logic gates to that bit, or read the value, like measure in which your quantum state is. So going back to our discussion on nonlinearity, so let's assume that we lowered the energy of our system by, for example, lowering the temperature or changing the current to the ground state. So let's assume that our Josephson junction is in its ground state. So if excite the Josephson junction by applying some certain frequency radiations, then what we have is an increase in the energy level of our Josephson junction, like so. So now we are at this state, but we keep on radiating the samples. Like we cannot control which energy state this will move to. So nonlinearity and unharmonic asked for. So superconducting Josephson junctions are perfect to use for qubits, and they are being used by various companies like IBM. And here we are looking at a transmon qubit. A transmon qubit is, we have talked about this actually, like they called it ultra small, but now we are using the term transmon here. Transmon achieves, I'm sorry, transmon qubits achieves its reduced sensitivity to charge noise by significantly increasing the ratio of the Josephson energy to charging energy. So that article was on good track when trying to understand the behaviors of these Josephson junctions. So here, unfortunately, we won't be able to talk about the detailed circuit analysis of real qubits like this, which is a rather complicated circuit, and it requires a high level of circuit quantum electrodynamics. But however, we now know that why we are using Josephson junctions as qubits and how we can measure or manipulate the state of the Josephson junction. And I hope that this explained and was beneficial for all of you understanding Josephson junctions. And that finalizes my talk for today. So thank you for listening, everybody.